For today's lesson, we're going to finish the equations in section 5-6. These equations are exponential equations that can be solved using logarithms. Earlier in the chapter, we had exponential equations where both sides could be written with the same base. In this case, 97 is not a power of 4, and there's no way to write both 4 and 97 as powers of the same number. So we need to use logarithms to solve. There's two methods to use when solving this type of equation. The first is to take the log of both sides. And when you do this, you can use common logs, natural logs, or really you could use any base, but for our purposes, I'm going to use the common log. So log of 4 to the x equals log of 97. The reason that we do this is that now that the 4 to the x is inside the logarithm, we can take this exponent and bring it out front as a coefficient. So x times log of 4 equals log of 97. And as you go through this, you need to remember that log of 4 and log of 97 are just numbers. So this is x times a number. I want to get x by itself, so I'm going to divide by that number on both sides. Now it says x equals log of 97 over log of 4. That's the only way I can write the exact form. If I want to get a decimal approximation, I'm going to open my calculator and I'm going to type in common log of 97 divided by common log of 4. And my value is, I'm going to round to the nearest hundredth, so 3.30. So this is one method for solving this equation. I'm going to do the same equation in a different method. And this will work well for most of you, especially if you have a TI-84 calculator that you're doing the work with. So our original equation was 4 to the x equals 97. I can take this equation, it's in exponential form, and I can change it to log form. So when I change it to log form, the base of the exponent is the base of the logarithm. The logarithm is equal to the exponent, so the x is going to go on the other side of the equation. So log base 4 of 97 equals x. And now this expression I can put into most of our calculators. Or if you have a TI-83 and cannot do so, you use change of base formula and you get back up to where we were before, log of 97 over log of 4. But remember, you can type logarithms if you go to math and down to the bottom to log base 4 of 97 should give us the same answer. There it is, 3.30. The second method is quicker as long as you know how to put this in your calculator correctly. And again, no matter what, you can put in your calculator. You just need to know change of base formula with the 83s. When you're solving these kinds of problems, you cannot go to logs until this base is isolated. So in a problem like this, 7 times 3 to the x, you cannot multiply the 7 times 3. You have to divide both sides by 7 first. So I get 3 to the x equals 29/7. And now I can go by either method that I used over here. I can either take the log of both sides, or I can change the log form. Again, if you change the log form, the base of the exponent is the base of the logarithm. Then I put the 29/7 as my argument, and that's equal to the exponent x. If you need to use change of base formula, it's log of 29/7, log of the argument, over log of 3. 29/7. Either of these, when put in your calculator, should give you the correct answer. Math, log base 3 of 29/7. Give me about 1.29, or again, I can do common log of 29/7 divided by common log of 3. Get the same answer. We're going to use this method to do a couple word problems. These are word problems where you're given in a situation that has an exponential equation in it. In this problem, we're given the resident population of the United States in 2015 was 320 million people, and it was growing at a rate of 0.7% per year. Assuming that the growth rate continues, the model for that is the population after t years is 320, that's our initial population in millions, times 1.007, that's 100% plus 0.7%. And the exponent is t minus 2015. That's the year minus the 2015 that we're starting in. But all we need to know is how to plug into this equation. The p is population in millions of people, and the year is t. The question says, according to this model, when will the population of the United States be 400 million? So my p is 400. So I'm going to plug p in here. 400 equals 320 times 1.007 to the t minus 2015. This is very similar to the problem we had here with the 7 times 3 to the x. So we're going to start off by dividing both sides by 320. And if we want, we can simplify that a little. It's 40 over 32, which ends up being 5/4. And my exponent is t minus 2015. So now I'm going to change this to log form. The base of the exponent is 1.07007. So that's going to be my base of my logarithm. The 5/4 is my argument, equals my exponent. So I'm going to take this logarithm, and then to solve for t, I'm going to have to add 2015 to that answer, and that'll give me t. So in my calculator, I'm going to take log base 1.007 of 5/4 and find that logarithm, and then I'm going to add 2015 to it. And the answer I get is 2046.98. So it's going to be at the very end of the year 2046. So maybe a good way to write this answer is by 2047, the population will be this high, because it's during the year 2046 that it's going to hit it. So that's showing how to solve this problem algebraically. You can also solve these problems graphically. So we're going to do this one where we're going to figure out when the population hits 435 million graphically. We're going to start with our equation. The current population is 435, and it's equal to our equation, 320 times 1.007 to the t minus 2015. In order to solve it graphically, I'm going to put one side of this equation in y1 and one side of the equation in y2. So I'm going to go to y equals, clear out all this other stuff. I'm going to put 435 into one side. And on the other side, my equation was 320 times 1.007 raised to the x minus 2015. So when we do this, we need to think about a good window. Our y-axis is the population, and we want to see where it crosses 435. So we need to go higher than that. And the starting population is at 320 here. And then x is the year. So we know it's going to be a number of years after 2015. And from our previous problem, we know that it's going to be after 2047. So when I set my window, I'm going to set my X-min, I'm going to set the minimum as 2015 because that was the first year. And let's go out to 2100, maybe. For the y-axis, population's above 0, and what we're looking for is where it hits 435, so let's go up to 450. Let's try that window. And I can see this pretty well here. It's going to hit right here. If you wanted to make the window go a little higher, might be a little better. We can see it increasing. So we want to figure out where that point of intersection is. So I go to calculate, option 5, intersect. First curve is the 435. Second is my population curve. Make a guess that's close by. And it hits at 2059.01. So we could have a whole discussion here about whether we should round down to 2059 or round up to the next full year. I think either answer would be fine in this case, but it's when is it going to be 435? By the year 2060. If you put 2059, I'd be good with that. These are the ways that you should be solving equations in the problems that are assigned for today.